Hello everyone, welcome back. So let's take a look at the electrostatics questions from the March 2025 paper. This is question number 8. I will link the solutions to the other questions in the top right corner of this video. So question number 8 reads, two small charged conducting spheres P and Q on insulated stands carry charges of -4 nanocoulombs and +12 nanocoulombs respectively. The centers of the spheres are 25 millimeters apart as indicated in the diagram. X is the midpoint, joining the centers. Again, 8.1, definition, we leave it out. Those are readily available. Question 8.2, calculate the magnitude. So magnitude means just give the value. The direction is not necessary. Of the resultant electric field at point X. So if you scroll to the electrostatics datasheet, you're going to have two equations for electric field. E equals kq over r squared, and E equals F divided by small q. Now, they want the resultant electric field. In other words, they want E net. Right? Now, we don't know anything about the force. So we have to use this equation. Okay? So we'll have to work out the electric field for each sphere, and afterward we'll have to combine them. Okay? Now, before we do this, let's look at the electric field pattern for positive and negative charge objects. For a negative charge object, the electric field pattern points toward the object. And for a positive, it points away from the object. Okay? So just keep that in mind. So 8.2.1, we're going to do, let's do sphere P first. We're going to say the electric field equals kq over r squared. K is 9 times 10 to the 9. The charge is 4. Well, we ignore the signs. When we use this equation and the force equation, we ignore the sign. So we're just going to take the magnitude. So 4 times 10 to the negative 9. Remember, NC means times 10 to the minus 9 coulombs. Divided by, now the distance is going to be half of 25. So 12,5. But 12,5 millimeters. So to convert to meters, divide by 1,000. So 12,5 over 1,000 and squared. So the electric field value here is going to be 230,400 NC. And now since this is a negative charge, it's going to point toward the charge. So it's going to be pointing to the left. Right? Now we'll do Q. So Q, E equals KQ divided by R squared. Again, 9 times 10 to the 9. Now Q has a charge of 12. So 12 times 10 to the negative 9 divided by, again, 12,5 all over 1,000 squared. And you get an answer of 691,200 NC. Now, since Q is positively charged, the electric field is going to point away from it. So that's going to be to the left again. So you can see that both these electric fields point to the left. So if you want the E net, the E net is just simply going to be the sum of them. So it's going to be 230, 400 plus 691, 200, and that's equal to 921,600 nanocoulombs. Now, we don't need to include the direction here since they only ask for the magnitude. Okay. Let's look at question 8.2.2. Calculate the force that an electron will experience at point X. So 8.2.2. So an electron, right? We're just going to take the absolute value, meaning we're not going to worry about the negative. So the charge of an electron, we'll just take it as 1.6 times 10 to the negative 19. All right? If you wanted to, you could use minus. I mean, it's not going to make a difference. I'll show you why. And we know E net. We worked it out, 921,600. Now, if we wanted the resultant force, in other words, we want F net, we can use the equation E net equals F net divided by Q. Now we want F net, so E net multiplied by Q is equal to F net. So 921,600. And again, here you could use minus 1.6 times 10 to the negative 19. You could use positive. It doesn't matter in this case because they want the magnitude of the force, right? The magnitude just tells us just the value. So you could sub in positive or negative here, it doesn't matter. So let's sub in negative times 10 to the negative 19. That's going to give me F net. And if you multiply those two values, you're going to get F net equaling minus 1,47 times 10 to the negative 13 newtons. Now remember, with a force, the negative gives you direction. They don't care about the direction in this question. They don't want the direction in this question. So just leave the answer as positive. So we'll say, therefore, the F net is 1,47 times 10 to the negative 13 newtons. Okay? Next, they tell us the two spheres are brought into contact with each other and then separated and moved back to their original positions. Determine the new charge. So this is grade 10, 8.3. Q new is going to be Q1 plus Q2 over 2. Now, the charges were negative 4 and plus 12. So it'll be negative 4 plus 12 over 2. That's going to be 4 NC. So this is going to be the charge that both of them have. So after contact, both P and Q will have that charge. They'll have a charge of 4 nanocoulombs. 8.4, calculate the amount of charge transferred upon contact. So in other words, we want to work out delta Q. So what is the change in the charge? So the change in the charge will be the final charge minus the initial charge. So here you could pick either one. It doesn't matter, right? Because the charge that's gained by P will be the charge that's lost by Q. Well, actually, in this case, it's going to be the charge that's gained by Q will be the charge that's lost by P. It doesn't matter which one you use, you still get the same answer. One will be positive, one will be negative. They just want to know how much. So again, it doesn't really matter. So let's use P. Doesn't matter here. So we'll say 4 minus 4. Right? So this is the final charge of P, and then minus the initial charge of P was minus 4. So that's going to be 8 nanocoulombs. So 8 nanocoulombs was transferred. So 8 nanocoulombs of charge was transferred. Question 8.5. Calculate the electrostatic force that the two spheres exert on each other after they make contact with each other and separated. So this is F is going to equal KQ1 Q2 over R squared. We know that K is 9 times 10 to the 9. And as I said earlier, once they come into contact with each other, both P and Q will have the same charge. So we can say 4 times 10 to the negative 9, and we can square it. because they both have the same charge. And then divided by, let's see the distance, and then separate, move back to original places. So they moved back to their original places, meaning the distance between them is again 25 millimeters. So 25 millimeters is 25 over 1,000 all squared. And put that in our calculator. That's going to be 2,3 times 10 to the negative 4 newtons of repulsion. And why repulsion? Because like charges will repel one another. If you enjoyed this video, please consider subscribing and like this video. Thank you.